A's an Archie who's a part poodle, part Rottweiler, who lives on Maple and belongs to Mr. Rumple. Then, for example, I have an Annette, who's an otter, who lives with a family near Elk River.
We wanted the name of birds.
I know, but the files are all organized alphabetically.
Lucy, go through the bird file.
No, you don't understand. They're organized alphabetically in the names of the pets.
We're gonna need some more coffee.
In this problem, we're going to answer the question, where is the tangent line to the graph of this equation, xy minus the natural log of xy equals y, vertical? Where does this curve have a vertical tangent line? Okay, so remember, from the unit circle, vertical tangent line, that happens exactly when the derivative is undefined because of a division by zero issue. So that's what we're going to be looking for. First, we need to compute the derivative. So it's the usual game. We're just going to take the derivative of that entire equation. So we'll have the derivative of the first piece, x times y. We'll have the derivative of natural log of xy. And then we'll have the derivative of the last piece, y, on the other side of the equal sign. Okay, derivative of x times y, that's using the product rule. We've seen that one before. Derivative of the first function times the second gives y. And then first function x times the derivative of the second will give dy dx. Okay, next up, the derivative of natural log of xy. That's a little more complicated. Using the chain rule, the derivative of the outside function is just going to be 1 over xy. That's because the derivative of natural log is just 1 over whatever the input is. But then we need to multiply by the derivative of the inside function xy. But check it out, we just computed the derivative of xy, so we can just use those same expressions there. We can just use the formula we found for the derivative of xy. I'm just subbing in there. Great, and then on the right-hand side, the derivative of y with respect to x, that's just what it is. It's the derivative we're after. Okay, this looks a little complicated. We have the derivative that we want 3 different times. That's what we're trying to solve for. I'm going to simplify things by multiplying the entire equation by xy. You don't need to do it this way, but it's just going to kind of clear things up. It'll make the algebra easier. So if I multiply everything by xy, what happens to the first term? We have xy times y, that's xy squared. And then we'll multiply this term by xy. That'll give us x squared y dy dx. Multiplying by xy here, that'll cancel with the 1 over xy. That was the whole point. I wanted to get rid of that in the denominator. So these terms just come along without any modification because we canceled that xy. And then finally we'll have xy times the derivative of y on the right-hand side of the equation. So now that looks a little bit nicer. Let's gather all the terms that involve the derivative on one side of the equation so that we can solve for it. So we'll have x squared y, we'll have minus x, and we'll have minus xy. I brought that term on the right-hand side over. And let's move everything else over to the right-hand side, so the minus y moves over, it becomes a y. And the only other term we haven't dealt with is the xy squared. When we move that over, it'll be a minus xy squared. Pretty cool. So that means the derivative is, by dividing by x squared y minus x minus xy, it's this expression right here. That's always going to tell you the derivative, the slope of the graph of this equation. That'll tell you the instantaneous rate of change of y with respect to x. Okay, but we're not done. Remember, we were supposed to find where the tangent line is vertical. And the tangent line will be vertical exactly when that expression is undefined. That's what we're after. So tangent line is vertical, not horizontal, vertical, when we have division by 0. So in other words, when the denominator in that expression is 0, giving us an ill-defined derivative. So in other words, that's true when x squared y minus x minus xy is equal to 0. So that's the expression that we need to solve for to figure out where the tangent line is vertical. Okay, I'm going to gather up the y's over here. What's being multiplied by y? We have an x squared, we have a minus x, that's it. And let's move the x over to the right-hand side, because then we'll get, by dividing everything by x squared minus x, we'll get x over x squared minus x. There's a common term of x on top and bottom, so it's easier to write that as 1 over x minus 1. I'm just canceling the x's there. Okay, great. So the tangent line is vertical exactly when y and x satisfy this relationship. But that doesn't really give us the actual points. That doesn't tell us the answer. So what do we do now to find the actual points? We need to sub into the original equation. If we sub this formula for y into the original equation, then we'll be able to solve for the actual points where the tangent line is vertical.
Hey, are there any more donuts? Sure. Andy.
Better wash that down with a cup of joe. I didn't get too much sleep last night.
Okay, so here I've written down again the original equation that we were given in the problem. And we just found that the tangent line will be vertical when y is equal to 1 over x minus 1. So I'm going to sub that expression in for the y's over here, okay? What do we get? When we put that for the y in xy, we'll have x over x minus 1, right? Multiplying this fraction by x just gives an x upstairs in the numerator. And then similarly, this xy, it's the same xy, right? The same logic. We'll get x over x minus 1 inside of the natural log. And then y, we're subbing in for y using 1 over x minus 1. Okay, great. So now we need to solve this for x. We need to solve for x. It's great that these have the same denominator. That's going to make everything easier. If we move the 1 over x minus 1 to the left-hand side and combine fractions, we'll end up with x minus 1 over x minus 1. I get that by moving this fraction, subtracting it from both sides, moving it to the left-hand side. And then the natural log I'll move to the right-hand side by adding the natural log of x over x minus 1 to both sides. So now we get this equation. Oh, but it's x minus 1 over x minus 1. That's just great because that is just 1, right? So in other words, what is this equation saying? It's saying that the natural log of x over x minus 1 is equal to 1. Now we have to remember our definition of the natural log. It's saying, what do I have to raise e to get x over x minus 1? And the answer to that question is 1. In other words, this is saying that e to the 1 is equal to x over x minus 1. That comes from the definition of the natural log here. You can also think about just taking e to the whatever on both sides. If I take e to the 1, I'll get e to the 1. And if I take e to the natural log, they cancel, and I'll just be left with x over x minus 1. Okay, we're almost there. E to the 1, that's just e. So once again, clearing the denominators, multiplying everything by x minus 1, I'll get e times x minus 1 equals x. And now gathering the x's, I'll have x times e over here, but then I'm bringing the x over as a minus 1. And now I have a minus e here. I'm going to add e to both sides, so I end up with an e on the right-hand side. And so finally, x is equal to e divided by e minus 1. What a funky number. That's the answer. That is where the tangent line is vertical. What's the corresponding y value? Remember, y was 1 over x minus 1, so I can sub in our formula for x, e over e minus 1 in the denominator. And we can make that look a little bit more reasonable. It doesn't have to look so absurd. If I write this as e minus, and then using a common base of e minus 1 to combine fractions like that, you'll see that the e's will cancel. I'll have an e minus e. I'm just left with positive 1. Two wrongs make a right in the numerator there. So this is 1 over e minus 1. In other words, that's just e minus 1. So at the end of the day, after all of that algebra, we have found that the tangent line is vertical at this point in the plane, e over e minus 1, comma, e minus 1. That's where the tangent line is vertical.
Because our world, the way I see it, has a lot of depth. And that's the way I like to see paintings.
In this problem, we're given the equation 2 cosine of x over y plus y equals 4. That has some graph, that creates some shape in the plane. Not necessarily the graph of a function, it's an implicitly defined function. And we want to evaluate the derivative at the point pi over 3. If you go and plug in x equals pi and y equals 3 in this equation, you'll see that it satisfies the equation. It's on the graph. So evaluating the derivative at pi over 3, that's telling us the slope of the tangent line to that graph at pi over 3. Well, in order to do that, we first need to find the derivative. And to find the derivative of this equation, we need to take the derivative of the entire equation. In other words, we need to take the derivative of both sides of the equation, like so. Okay, let's evaluate those derivatives. So here we have a chain rule because we're taking cosine of something. Okay, the derivative of the outside function cosine is minus sine. So we'll end up with minus 2 sine of the inside. But then we need to multiply by the derivative of the inside, the derivative of x over y. We'll do that in the next step. Let's just leave it there, writing it as a derivative. This term, the derivative of y, that is just dy by dx, the derivative by definition. Whereas the derivative of 4, it's a constant, so its derivative is 0. Okay, now, we need to evaluate this derivative of x over y. We'll do that using the quotient rule. Derivative of the top is just 1, so when we multiply it by the bottom, we'll get y. And then we subtract the top times the derivative of the bottom, dy by dx. And that's all divided by the bottom squared, y squared. So that whole entire fraction, that comes from the quotient rule for the derivative of x over y. Let's leave the dy by dx the same right there. Okay, now we just need to solve for dy by dx. Again, I'm going to do the trick where I clear the denominators to make the algebra easier. So let's multiply everything by y squared. I'm going to do that to get rid of this y squared. I don't want to deal with that. When we multiply by y squared, the first term will look like this, because of the y squared canceling. And then the second term will pick up a y squared, because we're multiplying by y squared. Looks good. And now we just need to gather all the terms that involve dy by dx. Okay, I'm in an algebra sort of mood. I'm feeling like I can do this pretty quickly. You might not want to do it as quick as me at home. That's okay. So what I'm going to do is I'm going to think about how this would FOIL out while I gather the terms. Check it out. What involves dy by dx? There will be a minus x times a minus 2 sine of xy. Two wrongs make a right, so I'll end up with 2 sine of x over y. That's the contribution to the dy by dx terms coming from this piece times that piece. I'll also have a plus y squared coming from the second term. And now since I want to solve for dy by dx, I'll take the other remaining term that we forgot about, that was minus 2 sine of xy times y, and I'll move it to the right-hand side, like so. Now I've accounted for all the terms, I'm ready to go, and I can just solve for dy by dx. What happens when I solve for dy by dx? I get a big old expression. I'm going to put the y out front before the sine. I think it looks a little bit prettier out there. So I get 2y sine of x over y, that's this term, and then I'm dividing by 2x sine of x over y plus y squared. So that's our formula for the derivative. We need to evaluate it at the point pi comma 3. That's what the problem asked us to do. So what does that mean Well, we're just plugging in pi and 3 for x and y. That's how you'd say this in Leibniz notation. We're evaluating where x is pi and y is 3. So I'm just going to plug all those values in. Let's see, so we said that y was 3, so that y becomes a 3. And then we have sine of x over y. X is pi, y is 3, so it's like that. And let's see, downstairs we have an x that's being evaluated at pi. And then we have sine of x over y, that's being evaluated at pi and at 3. Good. And then we have a y, which is a 3 being squared. Cool. So I've fully evaluated where x is pi and y is 3. What is this number? Got to remember our unit circle. What is the sine of pi over 3? What is the sine of pi over 3? It's the y-coordinates up near the top of the unit circle at that special angle pi over 3. The y-coordinate at that point is root 3 over 2. Got to know those values on the unit circle. Down here I'll have 2 pi times that same sine of pi over 3. And then I'm adding 9. Okay, let's simplify a little bit. Let's see, check it out. Downstairs there's a 2 here and there's a 2 here being multiplied. Those cancel. And I can also cancel a factor of 2 out of that 6. Let's do that. That looks good. So then up top we'll have 3 root 3. And then in the denominator, what's left is pi root 3 plus 9. Very nice. Let's leave it that way. That's the slope of the tangent line at the point pi comma 3.
Very sharp of what was back. No, yes, I had a friend. Yes, I thought it was very good against me. I can still be there. Sharp enough, and there's got was some fighting. I think it's not marked. Not in the sense. Not in the very and all the things. Not in the green lost and all. Or what? Mark the blue.